It's a pleasure for me today to introduce the two speakers, Vasyl Skorych. Actually, he's a managing director and head of development at Dyssolpro, but he's originally a computer engineering major at university in Ukraine, but then went to Germany for his PhD, exactly on dynamic flow sheet simulation of interconnected solid processes. So I think he is certainly the brain behind what we're going to be seeing today. But he's going to be joined by Christian Eichler, who's actually the managing director of Dyssolpro. And he actually studied process engineering at the university in Germany, Clausthal. And he got some industry experience and also pursued a PhD at University of Hamburg, which is really the alma mater of the Dysol and also of Dyssoltech. So it's really a pleasure for me to have you guys here at the GCC seminar to present a little bit of the Dysol Pro, which is a tool that we're very excited about inside the GCC. Please, guys, take the floor.
It's also a pleasure for us to be here today. And yeah, welcome from our side, to welcome you on behalf of the company Dyssoltech to today's seminar. Today we would like to present our company, Dyssoltech, so who we are, what we do, what we can do, following with a more detailed introduction of our flagship product, Dyssolpro. It's a tool for dynamic flow sheet simulation, especially designed to work with particulate solid materials. We will explain a bit about the origin of the tool, then go through the distinguishing features of the simulation tool that make it stand out from its competitors, following by the coming soon and new planned features aimed at simplifying the use and expanding the scope of the applicability of Dyssolpro. And finally, if we have enough time, we'll show a few usage examples from different application areas to give you a better understanding of the scope of applicability of the program. And at the end of course, we'll have a Q&A round. But yeah, before all of this, a short introduction round from our side. So who we are and where we come from. Yeah, I was already introduced. My name is Vasyl Skorych. I hold a master's degree in informatics and did a PhD in process engineering at the Institute of Solid Process Engineering and Particle Technology at Hamburg University of Technology, Germany. The topic of my PhD was the dynamic flow sheet simulation of solid processes. So basically, I invented and developed the first version of Dysol during my time in the Hamburg University of Technology. So it's no surprise that my main role in the company now is the development and programming. I'm responsible for the technical implementation of all the ideas that our team and our customers come up with. Yeah, the next important person in our team is Christian Eichler, who can probably introduce himself.
Yeah, most of it was already said. Christian Eichler, I studied process engineering, and yeah, my PhD topic is still about the it's pharmaceutical-based granulation process, and I use there two tools which I'm gonna introduce to you in a moment, and cover the integration. And my role at Dyssoltech is talking about the physics, so implementing the physics of the models, so developing models and the sales part. Besides Vasyl and me, also Sophia is on board. She comes also from the same institute, and Professor Heinrich, who's the head of the institute. So we all met there at this institute of Professor Stefan Heinrich. Yes. And with that, I'd like to jump into what are our processes, not our processes, our products. We have actually two types. We have a macro scale process line with our, Vasyl mentioned it already, flagship Dyssolpro. first, Dyssol. We say Dyssol usually in English terms. People say Dysol. Everything is fine. It stands for, or it's an acronym for Dynamic Simulation of Solids Processes. So focusing on solids. However, we can map also liquids. We can map gases. But the solids is the main part, and the dynamics is the main part. Besides that, we are working on making it as easy as possible to use, that our clients and any user has the fastest onboarding and does not require any special training to get used to this software. That's why we are constantly improving the GUI, etc. And all future implementations in Dyssol will go into the Dyssolpro branch, because we have also another branch, the Dyssol here. It's also called Dyssol Open. It's an open source code, and it's the fundament of Dyssolpro. It contains the main simulator, and it has a rough limited GUI, which is, for our industry partners, do not like it too much, and it's more practical and more for the scientific use, since Dyssolpro is for the industry. Okay, you can check it out if you want. Just search for Dyssol and GitHub. You can download it and test it if you'd like to. Besides this macro scale simulator, we also have a micro scale simulator. It's called Musen, and it's a DEM software. So DEM stands for Discrete Element Method. And what is very unique to this simulator is that it is a open source tool which has the GPU acceleration of CUDA. So you can run fast, or you can accelerate your simulations on GPUs if you have one, and the GPU limits then the amount of particles you simulate up to several millions. What also comes with Musen is a bonded particle model, where you can connect several particles via bonds, and these new generated connected particles can form any sort of aggregate you'd like to. It's also developed at the TUHH and mainly by Vasyl, so he's really the brain behind all of our products. And currently we maintain the software, so we as Dyssoltech. Since it's open source, we cannot track who's using it, but due to the requests we receive, we know that it's applied in industry and academia, and we have several projects ongoing with DEM, with this DEM tool as well. But our target is to keep this tool open source, and all changes we implement for the industry are also published in the open source code. Okay, for now we have many open source tools and actually not too much products to sell. However, we have Dyssolpro, and we'd like to sell this, or we do sell this already. And our business model contains two parts: the licensing of Dyssolpro and services. Within the service part, we develop custom models. Of course, we have already some, but as you know, models can always be better. And for instance, GCC wants to implement more precise models. And we can help them. Of course, we do not have this knowledge to generate them, but we can help them. And also for just basic models, we take over the responsibility for our clients. Besides that, we do general consultancy around our tools. And of course, we offer training that we enable our clients to implement their own models, because actually that's a nice target if they if they can implement their models, and we do not have too much contact points, and it's a living environment, let's say, with a large community. So all of our simulators are focusing on solids, right? The DEM focusing on particles, which you can track, and Dyssolpro focusing on particles as well. So our target markets are actually all industries where particles are involved. And currently our main partners and clients are in the chemical sector, but also we see a growing interest in the food and pharma industry, as well as in the concrete production and concrete plants. And I wouldn't say it's increasing, but we have constant projects with the recycling industry. And today, yeah, as we are in the GCC and this is focusing mainly on mining, we are targeting mining. But since we are coming from a more process engineering side, we haven't focused on mining too much yet. So, and we want to shift there a little bit. And with that, Vasyl takes over to tell you a little bit more about the milestones of Dyssolpro.
Yeah, before we dig into the features of Dyssolpro, I would like to go a little bit through the history of its development, because it has quite a long one already. Because back in time, there were some tools available for the process simulations, but they were directed only for the liquid process, mostly for chemical and petrochemical industries. And so there was a lack of such tools for solid materials. So back in time, even before Dyssolpro, the professors from the TUHH, from the Technical University of Hamburg, decided to fill this gap, and did the first attempt to create a generally applicable tool for process simulation of particulate solid materials. But that tool was only limited to the investigation of the stationary behavior of the process. So in 2012, a second iteration has started, a research project founded by the German Research Foundation. The idea was to enable the process simulation with extended consideration of the solid phase and the consideration of the dynamics of those processes. It was quite a large project consisting of about 30 different research groups from about 15 universities and institutes all over Germany. And they were working on the development of new dynamic models for the solids production industry, of new methods and algorithms to treat them, to measure them, to model them. And the job of the group in the Hamburg University of Technology, and basically my job, was to integrate the results of all these groups together into a single simulation environment to enable this modeling of the solids process in the same way as it was already established back in time for the liquid process. And this was the origin of the Dyssolpro tool. So at the end of this project, of this publicly funded project, the first version of Dyssolpro emerged, which is currently the Dyssolpro version, this open source version, which is still available there for the whole research institutes and the community. And already with this purely academia version of Dyssolpro, we had a few early adopters of the tool who introduced this program in their companies. First of all, this is the Vasyl, the largest chemical producer here, and I think in the world. They took Dyssolpro, and we had back in time some research projects together, and they also introduced that in the research and development team. And based on this, there was a need to have some backup for this tool, and that's why that was one of the reasons why we have founded a Dyssolpro company to provide such companies as Vasyl maintenance, the professional and a professional and constant maintenance of the tool to develop this product further on the commercial rails, and to provide help and introduce new features. One of the first projects after the foundation of the company was our industrial consortium where the BASF and another chemical company, Evonik, were involved. The idea was to get the input from the industry to have the correct direction in the further development, in the further implementations of features. So we gathered the input from the industry to understand what features do they need, what is lacking in the tool, how we should progress further with our tool. And this was a pretty successful collaboration between three of us, so Dyssoltech and BASF and Evonik, where we, as a result, actually, we have our first Dyssolpro version release this year, actually, in the beginning of this year. So this Dyssolpro version contains all the new features we have developed since the foundation of Dyssol. And currently, we have running some other projects with the industry and also with the academia. One of those projects is the cooperation with the group of Professor Lieberwirt from the ERT Institute. It's basically our first big commitment in the German mining and aggregates industry. Yeah, next. So, yeah, actually, the first thing we did after founding the company is completely rework the user interface of the program, because that was the major like pain from the early adopters, from all the users, to make it look and work the same as other simulation tools there on the market. So currently, it is intuitive, easy to work with. One sees the whole process which one creates. One has the library of models where one can access to drag the models from this library onto the working area, build the flow sheet by connecting them, those models together with some material streams, also graphically on this tool. And from there, one can access all the settings of the simulation, all the model parameters, and one can run the simulation and see the simulation results there in the same window. Of course, despite it is fully functional now, we are still constantly working on the improvements here, because the simplicity of the interface of the user interaction with the program is extremely important. So we constantly introducing new features and new simplifications, and constantly working in this direction also. So I already mentioned one of the main features. One of the main features of Dyssol is the treatment of the granular solid phase. It's basically one of the distinguishing features of Dyssol, which is only done by us, because usually when, of course, there are some tools which also can work with solid materials, but what they usually do, they only consider the particle size distribution, which is clear, because it's one of the most used, one of the most important properties of our granules. Yeah? But what we do in Dyssol, we allow to introduce different distributed properties. So we can say we have not only the particles of different sizes, but those particles can have different porosities, different Young's modulus, different forms, because all these properties of the material do have influence on the process behavior, do have influence on the properties of the final product. So it is very important to be able to consider them properly. And in Dyssol, we can do this by building so-called multi-dimensional distributed properties and considering them in the models. which is unfortunately, or okay, fortunately for us, because we did it, it's not so easy to do. Just because of this interconnection between the properties. To explain this a little bit, we brought this a very simple example of the screening process where we can introduce, for example, there are two materials. We can say the material A, this red material, has diameter of 5 millimeters. So the particles of this material have a diameter of 5 millimeters, and the other blue material is these are smaller particles of 3 millimeters. So we mix them together in the proportion 1:1 and put into the screen unit. Yeah. If we do this in our real process, we understand, we know what will happen. Yeah, after the end of the process, we will get, given the good screen performance, we will obtain the ideal splitting of these two parameters. So we have the large red particles separated from the small blue particles. But when we create a model, when we write our equations to model the process, we usually only consider those parameters which are critical, which are important for the model we are working with. For the screen unit, for the screen model, it will be particle size, because the screen only decides based on the particle size in what fraction those particles will land. And for the model, as of when we create this model, we don't actually care about whether those particles have different colors or whether they have different densities, okay, in most of the cases, or other properties. So if we just simply apply the normal screening model for this very simple example, we obtain something like this, probably, because the model, this mathematical formulation, does not allow us to say what to do with, in this case, colors. How do they split based on the size? But of course, we know that the color is bound to the sizes of the particles, and that is what Dyssolpro can actually treat. We can do treatment of the multidimensionally distributed dependent properties correctly in our models. What we can do if we have this implemented in the models is the following example, where we have the next one. So it's a very simple example from the pharmaceutical industry, where they have two materials, coming from two feeders. The one material might have smaller particles with some concentration of the active ingredient. Another feeder feeds another type of material with another concentration of active material F and of another size, so with a little bit larger particles. Then we mix them together and put into an agglomerator where those different particles stick together, forming larger agglomerates, larger particles. By this, the size of the particle changes, and of course also the concentration of this active ingredient changes in the overall agglomerate. And to control the size, to control the final sizes, we have a screen mill cycle attached to the agglomerator where the particles are separated by the size, and the coarse fraction is crushed in the mill and returned back to into agglomerator to grow further. And of course, in the agglomerator here, since it should take into account both particle sizes and the concentration of the material, because concentration of the active ingredient, because when the particles stick together, both change. So we have to do this explicitly in the model. But the rest of the models, the screen and the mill, they can apply this approach which Dyssolpro provides to actually only explicitly take into account the particle size changes. So the screen will separate the particles by the size, the mill will reduce the size of the particles, but still the secondary property, this API concentration, will be bound to the size and will be preserved properly within the whole flowsheet simulation. So at the end of the simulation, we can still track the changes of both distributed properties of how the particle sizes change because of the mixing, agglomeration, screening, and milling, and how the API concentration changes because of the agglomeration in the agglomerator device. Of course, since we do this dynamically, we can see how those parameters change over time. Yeah. Another important thing what the Dyssolpro provides is flexibility by the development of the models. So what the people usually do in the industry when they develop the models, they basically they write the equations. Yeah, the equation which describe how the device changes the properties of our material. This can be done with different types of equations, but then when we build a flow sheet, what the people do, they just took all the equations, plug those equations into a single large equation system and solve them together. Sure, that works, that is simple, but it is not flexible at all because we are bound to those types of equations we can combine together. And this is the problem in the solids area because our models are very difficult. And from the other side, we want to give a possibility for third-party developers or even the users of the program to write their own models, to extend the model library. And that's why the Dyssolpro follows a different approach. In our case, every model on the flow sheet is independent from the rest. So the flow sheet system gives the model the information about the properties of the material which comes into the unit, some settings, some of the model parameters which a user can change, and then say, do what you want. Do what you want inside, just give me the results back, the results in terms of properties of the materials, new properties of these materials. And this allows the large flexibility of the tool, because now for the simulation system, it doesn't matter what is happening inside the unit. Yeah, we can still use some usual differential equations or population balance equations there, but we also can integrate some black box model there, like data-driven models or AI models, or even couple directly from the unit to other simulation tools, like doing microscale simulations during the flow sheet run. And we can even combine those white box and black box models together, building a gray box and integrate it into a single model. And then on the flow sheet level, we can combine all those different types of models together, and they still will work together, providing the solution of our problem. Of course, for the user, it is also easier then to develop those new models because there is no boundaries. There is much more flexibility in terms what can be done, what type of the model can be developed, what methods, what algorithms can be used inside. Yeah. Yeah, and another important feature, of course, is the dynamics. So the point is, yeah, we can do what our competitors do. They provide the way to calculate the process, the steady state of the process. Means we plug some input into the process, we obtain one output at the end of the process. But there is no possibility to see how this output was achieved, how time it takes to achieve this output, what is happening inside the process after we set those materials into the process. Whether we overshoot some target values during this setup, during this startup, whether we use more energy or more material that we have, or something like this. And that is exactly what Dyssolpro can help with, because it allows us to simulate our processes dynamically, so taking the time into account. So we can basically track what is happening in the process when we, for example, turn on the process. What happens when some clogging occurs in the process, when something stops, how the process behaves over time. this allows us to model the batch process, for example, where we have just a device, plug some material into, close the cap, and turn it on and wait, until the material changes there. This is what can be done with the dynamic simulations in Dyssolpro. And this gives us a wide range of different possibilities to investigate, to deeply investigate the process. To explain this a little bit, we brought this very common example from our industry, from where we come from. This is the granulation process, very commonly used to produce fertilizers. So the main model here, the main unit here is the granulator, so it's just a container basically, where we have some material inside, the granules inside of different sizes, so particles of different sizes. We spray in some suspension there, which contains usually water and the solid part. Those suspension covers the particles inside the device. Then we have the fluidization gas from below the unit, which make the particles move inside and mix. So the particles are getting covered by the suspension. Then, since the gas is hot, the water is evaporating, and the solid part stays on the particle, so that the particle growth occurs. By this we can increase the size of our material. And to control this size, we have the typical screen mill loop attached to the granulator, where the particles which are too large after the granulation are crushed there and returned back, mixed with the particles which are too small, and these are returned back to the granulator, and those small particles act as a new nuclei to start the new growth process. And the point for this process is sometimes it can behave unstable, and that is what we cannot investigate having only the steady-state simulations. And there where the Dyssolpro comes in handy, because it can predict and it can model such dynamic behavior of this process. Christian?
Yes. And it's nice that we can simulate these oscillations now. However, you can ask yourself, if it's really your process, you actually do not want these oscillations. You want a steady state process, and you want to get as fast as you can. Well, you want to reach this steady state as fast as you can. And one possibility to do that is to perform a sensitivity analysis. That's also an inbuilt tool, which I want to mention and come back to this example later. So the sensitivity analysis usually works like a DOE, so a design of experiment. You perform samples at different tests, at different inputs, and you receive results. And we have the same here. Imagine this is your process. Everything you can change. You can change also. You can change also in Dyssolpro, like the mass flows which going into the flow sheet. You can also change the composition of the mass flow. You can change actually even material parameters. If you have a natural product going into your process, it may change in its strength, etc., etc., and this might influence the process in somehow. All this you can set. Also, you can set the parameters of your process, e.g., what's inside of the process here, like the hold up. The hold up is the bucket in which all the material is inside. Let's put it in that way for dynamic units. Or if you have a mill or a crusher, the power or the rotational speed, and of course, if you have a screen, the screen deck size, or a sifter, you can set the RPM of the wheel, etc., etc. All these parameters you can vary, and you measure then the parameters of streams mostly streams, like the composition, the mass flow, the particle size, temperature, pressure, all that you can measure. And additionally to that, you can measure internal values or variables of units. So probably you are interested in the temperature of a certain position in the crusher. You can also detect that if it's inside the model, of course. And when we come back to this example, the only thing we'd like to change here, for the sake of simplicity, is the power of this crusher. And when we look on the time it spends until the whole process got steady state, it took like half a day, like 12 hours at a power of 7 kilowatts. And now we just perform some simulations using the sensitivity analyzing tool. We also have a look on this throughput over the mill, which could also be interesting. And then we perform, in this case, not lots of simulations, but a couple of them, and you receive immediately the result. And of course, you can imagine like adding more and more parameters you'd like to vary, and then you make a full factorial analysis, and you can analyze the data later on. As you can see here, by decreasing the mill power, at some point you even reach a minimum time to get into the steady state. However, it comes with the downside that your mill throughput increases by decreasing the mill power. So the sensitivity analysis tool is actually a tool to run a massive amount of simulations just by one click. And you receive the results, and probably you'd like to analyze the data later on in your specific analyzing tool, like, I don't know, Excel, Minitab, etc., etc. Okay, I think we have to hurry up a little bit. Another tool is the optimizer. And of course, with the sensitivity analysis, you can achieve some optimum, but that was an easy example. When the objective becomes more complex and more parameters you'd like to adjust, then the optimizer comes into place. So in this easy example, we have just set the objective function to the production mass flow, increase the mass flow here. You may increase the input as well. You can change the filling level here, and you can change the power. If you think about it, of course, increase the input as much as you can, and you receive also the output as high as possible. It comes with a constraint, the yellow part here. This pipe, we can consider it as a, I don't know, pneumatic transport system, which can only transport a limited amount of material. And with this constraint, and of course, we set some boundary conditions where, for instance, the input, you can't put as much as you want. It's limited by the pipe size, etc., etc. You set the boundaries, constraints, and then you click on optimize, and Dyssolpro runs many simulations trying to optimize the product output, considering all these boundaries and constraints. And here in this example, you see after around 70 iterations, the conditions were already quite stable. And of course, you can build more complex objective functions, including energy consumption, including other streams. You're free to define these objectives. Okay. Sensitivity analyzing and simulating all these processes is actually only interesting if your models are quite accurate. And you have to prove that your models are calibrated. And to calibrate these models, we have the parameter estimator. And this tool is also kind of an optimizer. In this case, I brought you a very simple screen mill circle. And we have 3 different positions where we measured some particle size distributions, and we have no clue which parameters we should set in these models. Probably these models are far away from the actual implemented use. So this is maybe a very simple crushing unit, but actually you have a very complex multi-stage crusher, but you just want to keep it simple. And you can now run many simulations varying these parameters of these two units. And you see after a couple of simulations, you decrease already the error, which is measured in these two particle size distributions. So this is measured, and then compared to the simulated results. And in the end, you receive here on the right-hand side a very close agreement between the measured values, between the measured particle size distribution and the fitted variables, and then the result of it. You see here mass fractions in the particle size distribution. You could also have cumulative distributions or density distributions. It's just here in this example. Okay, so calibrating models is a tool, and optimizing a tool, and run a massive amount of simulations is the other one. Okay. In the next part, we'd like to show you very briefly, the upcoming topics we are working on.
Yeah, one of those features we currently plan for next releases of Dyssolpro is the containerization of the program, which should speed up and simplify the introduction of and adoption of the program by our clients. There are two main parts of this process. The first one, which will ship Dyssolpro as a Docker container instead of the usual installer, so that this container will already contain all the Dyssolpro itself and all the tools needed to run it, which is especially important on the Linux platforms. But this allows us to not only put the Dyssolpro there, but also some pre-configured flow sheets, which we can then ship together, so that the user can only have to only run this Dyssolpro container using the Docker environment to obtain the simulation results. The next step would be to create a simplified web interface dedicated to this specific process, where since we already know what process we are simulating, we can introduce some input parameters there, only a few of them which are most important, and then have the outputs, which is important for this process, shown at the same web page. And then this web page will communicate with the Docker container by pushing there the user input of these inputs and running the simulation and returning the results, which will be shown by the server here. So by doing this, not only the R&D department of the companies will be could work with the Dyssolpro, but also the operators, so that could decrease the startup time, could allow to better control and output the output of the process, and decrease the shutdown times of the equipment. We are currently rolling out these features to one of our customers from the chemical industry, and soon it should be available in the for other customers. The other thing is, historically, the Dyssolpro was developed using the C++ language, and that's what we use when we create the models, because it gives us the possibility to maximize the performance of the calculations. But as I already mentioned, we want also to introduce this possibility to develop the models to our customers, so they can come up with a fast prototyping with their own processes. And this, of course, is very tedious to do with the C++, because not a lot of people can do this. Therefore, we plan to integrate, so we are currently working already on this feature, to integrate the Python scripting language to Dyssolpro, so that the new models could actually be created using the Python completely, without the need to dig into this complicated C++ programming language. This will also allow to, first of all, to create the models themselves, as complicated as it is needed, because the Python already has a lot of different modules and libraries for different stuff. And also it will allow to connect those models to some external tools, for example, if needed to do some additional operations which are not provided by Dyssolpro, for example. The next step from this would be to wrap up the whole Dyssolpro into a Python model and ship it as a Python model. On the one side, this will allow to run the Dyssolpro simulations completely headless without the use of the graphical user interface if needed. So in the Python script, we'll be able to introduce the whole flow sheet structure, all the settings, all the model parameters we need, run the simulation from the Python script, and then obtain the results after read the results after the simulation is finished. But on the other side, it will also allow us to couple Dyssolpro with other tools, because we know that any tool, even Dyssolpro, cannot provide all the possibilities, cannot cover all the needs of the industry. So it's often needed to combine several tools together. And providing Dyssolpro as a Python library will allow to use Python as like an orchestrator to run different tools and connect them together using this Python interface.
And since we got already some feedback from GCC, and we have the collaboration together with Professor Lieberwitz Institute, the ERIT, we are currently working on controllers. And it's still in the early stage of development, but our focus and our plan is here to have a controller which has not, of course, can have this standard input like the PID controller or a simple switch on off. But also you can build their complex control strategies and functions, take them from different stream or different units, or even this would be the next step, connect external servers to your controllers, get the input, to control a unit or use it as a signal for other logical units, which will be also implemented, like integration differentiate some. Maybe you need more and we can put more in there. It's just very brief. And this is the last slide we're going to present. Within this frame of GCC, where we are currently, the idea was that GCC, of course, implements or develops models, and one possible opportunity is to combine all these models within one platform is Dyssolpro. And Dyssolpro is nice in that terms that you have already done these GCC models, but also you can develop your own models and use, of course, the built-in library and all these models which are already available within Dyssolpro. And we are, of course, continuing working on them and adding more. Plus all the connectivity features and additional features which are inside of Dyssolpro, why we are happy to collaborate with GCC, because we can develop features which are required for the industry, and I think everyone wins when a tool becomes super handy for industry and super nice and easy usable. Okay, so I think we have 10 minutes for questions, because we're gonna skip the examples. However, we can stay for a little bit longer in this talk and answer further questions or go through the examples, of course. Thank you very much.
Thank you, Christian. Thank you, Vasyl. Very interesting presentation. We have time for some questions from the audience. So, have any questions? Just open the mic and speak up.
Hello, everyone. It's Paul Shelley. How's everybody? Great. Just got a question for the team. So thanks very much. I'm like really interested in this. there are two things going on. So in our world, and there is like a point in time analysis where you are essentially looking backward. You've got all the data and it's coming in, and you're looking backwards, and that's valuable, and that can generate that consulting revenue that you put in the model, that you put at the front, consulting, because you can analyze these circuits, getting the real data using, like, for example, you might use a liner campaign, or you might use two liner campaign, or these types of things. And then there's this real time where it's dynamic, like you've described. Have you thought about, like, can you make comments about where that split is, or what you're thinking in that space? Yeah, that is it an understandable question?
You're talking about using the data, historical data, to analyze and predict the further process conditions, right? Did I get it right?
I was talking about using that historical data in a consulting sense.
Yeah, but
So,
I mean, we can do. That's actually what we can do. Yes, we can do. We can use the historical data and then extract some information from there. We can build some kind of data-driven models which can predict, yeah, for us something. The problem is here, I mean, that it's very interesting and also a possible way of work. But the point here, it is a very targeted solution for a single company, for a single customer, because we cannot use the same data obtained from the industry to train or to use and use them to provide solutions for other companies, because the companies are very usually very closed, yeah, on their data. They do not want to share them, and if they share, then only for the purposes to work with this exact company. So yes, possible, can be done, but the approach is not very scalable, and it puts some higher price tag on this solution, probably.
Malcolm?
Thanks, Vasyl and Christian. It's really nice to get that catch up, and when we encountered you some years ago, how far you've got. I'm quite interested in the data output side, because you mentioned that you can link it through Python and link it to output sources. A lot of people still use Excel and things like that. Do you have a pretty basic data dump format that, like a simple structure that's consistent, one can dump out and analyze, or will one need to use something like Python code to pull out the outputs and graph them as you want and things?
There are 2 or even 3 possibilities currently. I mean, apart from using the just graphical user interface, which of course can be tedious. These 2, which we are working on with the Python, which will allow us to format the output data as we want, basically. And we also have another running project where we want to implement the XML output, so XML formatted output from the simulations, which basically will do what you say. Yeah, it will be structured, it will be described properly, and can be analyzed also automatically by some other tools, Python or whatever. Did it answer the question?
Yeah, it does. It's just very useful to you, because then instead of trying to build it all into your software, you hand it over the fence and we do it in any way we want. Thanks, Vasyl.
Yeah. But of course, it will require the understanding of the format, which we will plug in. But it will be standardized and hopefully fixed for a long time.
Yep.
Gauti has a question.
Yeah, I'm just a little curious about the optimization. What kind of approach are you using? If it's brute forcing or gradient based or non-gradient based, or how are you finding an optimum?
Since we are, as I shown before, yeah, since we are using this modular approach for the calculations, and we are discretizing time, in time, we cannot use the gradient-based approaches. So it's approaches without gradients only we can apply to. And basically, these are some global optimization procedure algorithms there. So it's not the try and false or sensitivity analysis thing. So the algorithm based on non-gradient optimization.
But still a global search, not a local search.
We do use. I mean, we tend to use the global search, but in some cases we can combine like the global search strategy with some local search algorithms in some places, so to say, and then combine them together with a global search algorithm.
Okay, good. Thank you.
Shujat, also a question.
Yeah, I got one. Firstly, thank you, Vasyl, Christian, great talk. Just reflecting on the last slide, but just trying to understand the application that is being worked on in the space of process control. Is it just PID loop tuning, or is it more than that is currently worked on? Yeah, here, that one. Is it just like a selection of right parameters for loop tuning and looking at models? Can you please talk a bit more on that?
Actually, our idea was, yes, to tune. By loop tuning, you mean to parameterize your controller function, right?
Yeah, right.
Yeah. That's the idea, to optimize your controller. I mean, when you have a dynamic process, you can control several units and again decrease probably the startup time, etc. Yes, and of course you can test different functions.
Right. So essentially, you're trying to minimize the error that you get, like because of any variable change in the actual process.
This would be combined then with the optimizer, for instance, if you want to. But this is now totally extra. So it's just in the simulation framework. It's not connected with the real process.
Okay.
Of course, you can then you can connect it somehow to real data later on if you like to. However, if you grab these data here as 0 and as 1, for instance, you also have to grab this stream here, which goes into your mill to have the right behavior within this mill. But if you are that far that you have a pretty good model, for the whole process, you can of course connect the real data directly into this controller to predict probably the future for a while. This is,
right.
I would say, that takes a couple of more months to years to implement.
Cool. Thank you.
Yeah, sure.
So we have time for one last question here from Anderson.
Yeah. Hello, Vasyl. I'm already a user from Dyssolpro. I bought it for a couple of years back in the version, so probably with the open one. So normally I work only with, let's say, customized units that I develop myself. So I'm interested in the parameter estimator. Can I use it to estimate material parameters like that is exclusive to my unit? Let's say it have a material property that's not a standard, like it's a very specific to one model. Can I use the parameter estimator to let's say to back calculate this parameter, or only like results, or like a process results or something?
Interesting point. actually, in the current version, it is not foreseen to do something like this, to have the material properties as the output of the parameter estimator. But I mean, it's an interesting idea. I kind of didn't think about it. But so not in the standard ways, but I think we can come up with the idea how we can do this even with the current version, with some with a couple of tricks, so to say. We could be able to do this also.
Yeah, because for example, what I normally do is when I have a unit in Dysol, I have, let's say, a twin unit in Python, and I use the one in Python to estimate my parameter. Let's say I have one parameter that I cannot characterize, so I back calculate using the unit in Python. When I get a good parameter, okay, now I apply it in Dysol. That's what I normally do.
I mean, theoretically, you can do this also now with the parameter estimator, but you will need to introduce kind of additional model parameter, which you will estimate then, which will be responsible for a model, for a material property value. So yeah, we can find a way for this. Yeah.
Okay, thanks.
Thank you, Vasyl. Thank you, Christian, for the very interesting presentation and discussions here today. So I think this is the last GCC seminar of the first semester. We have now a break in July, and we will be back in August with, by the end of August, with Professor Tim Napier-Moon presenting the GCC seminar. So thank you all for joining us today, and this recording will be available on our YouTube channel in maybe tomorrow. Okay, so thank you very much for joining, and thank you, Vasyl and Christian, again for the very interesting talk.
Thank you very much for having us.
Bye
Thank
now.
you very
Thanks a lot.
Thank you.
Thank you.
Okay, bye.
Cheers,
Thank
everyone.
you.
Thank you. Bye.
Thank you, guys.
Bye.